Hello, welcome back. Today we're going to talk about isotopes and relative atomic mass. And we're going to start with a little review, and then we'll get into some calculations today and how to do those. If we have time, we might move on to the HL content, which is about mass spectroscopy, which is a really cool technique that chemists use to determine isotopes and other things within a sample. We'll see if we get to that. Let's look at this. How many protons, neutrons, and electrons are in each of these atoms? So we have them with the notation that we learned in our last lesson. I want you to take a moment, pause the video, and write down how many protons, neutrons, and electrons are in each of these atoms. Okay, so let's start with this first one. Carbon, right? 6 is its atomic number, so it has 6 protons. Neutrons you can find by doing the mass number minus 6, so that would be 6 neutrons. And because there's no charge, we know the electrons are also equal to the protons, so 6 protons, 6 neutrons, 6 electrons. For helium, right, 2 is its atomic number, so we have 2 protons. The mass number minus 2 is 2, so 2 neutrons, and then 2 electrons. Beryllium is an ion, right? It's 2 plus ion, so it has 2 less electrons than it does protons, so it's going to have 4 protons, 2 electrons, and 5 neutrons. This fluorine is not an ion, so we have 9 protons, 9 electrons, and 10 neutrons. The copper, let's see, it has 29 protons. It has 29 electrons because it's not an ion. And then 63 minus 29 is what, 34? So it's 34 neutrons. This oxygen is an ion. It has 2 extra electrons, so it has 8 protons, 10 electrons, and 8 neutrons. So, I would like you to find the average mass of a dog in this group. And we have a group of dog that contains 32 Shih Tzus that are 8 kilograms each. We have 58 Pomeranians, which are 13 kilograms each, and 10 Burmese Mountain Dogs, which are 38 kilograms each. What is the average mass of a dog for this group? See if you can figure that out. So pause the video, take a minute. Calculate the average mass of a dog in this group. Okay, so the answer I will give to you, and then I'll explain how you should have done it, is 13.9 kilograms. You can get this by multiplying the amount of dogs you have by their weight, right? And then adding that to the next thing. So you do 32 times 8, because there's 32 Shih Tzus, they're 8 kilograms each. Then you do plus 58 Pomeranians times 13 kilograms each, plus 10 times 38, and then you divide that entire thing by 100, and you get your average weight, right? Your average mass, which is 13.9. And this is called a weighted average that we're doing here. And the reason that we divide by 100, right, in this case, is because we have 100 different dogs. If we add these all up, right, 32 plus 58 is 90, plus 10 is 100. That's why we divide it by 100. So that's a weighted average, and that tells you the average mass of any given dog within this group. We're going to use this technique when we look at isotopes. So what are isotopes? We have three representations of 3 different isotopes. From this, can you discern what an isotope is? So take a second, think about it. Write down what you think an isotope is. So isotopes, we can see, let's look at what's similar and what's different between these. Similarities, right? It's all hydrogen. They all have 1 proton. and H, hydrogen. These are all types of hydrogen, but their difference is that they have different mass numbers, which means they have different amounts of neutrons, right? So isotopes are atoms of the same element, so the same number of protons, with different mass numbers or different amounts of neutrons. Here's another way to represent each of these, right? So hydrogen 1 has one proton, so a mass number of 1. Hydrogen 2 has a proton and a neutron, so that is two things in the nucleus, a mass number of 2. Hydrogen 3 has a proton and two neutrons, which is three things in the nucleus. For hydrogen, these isotopes get special names, which this first one we just call hydrogen, the next one we call deuterium, 2, and the third one we call tritium, for three things in the nucleus. A lot of isotopes, excuse me, I'm gonna take a drink, don't have like super special names like this, right? We just call them their element name and then their mass number is how we name them often. So, properties of isotopes. We have some things over here, right? Chemical properties, physical properties. You can see on this that the physical properties are different. So, chemical properties end up remaining the same because chemical properties are largely due to the electrons that are orbiting around the nucleus, and because they all have the same amount of electrons, they are all have the same reactivity roughly. The physical properties, however, can change because the weight of the isotopes is different. So, like melting and boiling points can be affected by this weight difference, and you can see that here on our table, right? The boiling and melting points are going up as they get heavier. And you can think about why that might be. If we think about the forces that are interacting, things with mass are attracted to each other, right? That's gravity. The heavier something is, the more attraction there will be between these things, and so that results in a slight increase in these melting and boiling points. So let's talk about the notation that gets used on the periodic table. Here we have the nuclear notation, which we've been using for different isotopes of lithium, right? We have its protons, and then we have its neutrons. When you look on the periodic table, you will see this, right? You have lithium. This 3 up here is the atomic number, or the amount of protons, which we usually put down here. This right here is an atomic mass, but it doesn't match any of these, right? Why does this not match any of these isotopes? These are the stable isotopes for lithium. This is different. So take a second, think about why that might be different. So this is different because this is not a single isotope. This is telling us about all of the isotopes. So this is a weighted average telling us that like if you have 1 mole of lithium, which is like a certain amount, it's a bunch of atoms, 6.02 times 10 to the 23rd atoms of lithium, it would weigh 6.94 grams, right? And that comes from these isotopes. And each of these isotopes has an abundance, right? So I'm going to throw up the next, there's a lot of things on here. The next slide. If we look at these different isotopes, lithium 6 is 7% abundant. So that means in a sample of 100 lithium atoms that you randomly pull from a like lithium ore, let's say, 7 of them would be lithium 6. 92 of them would be lithium 7, and 1 of them would be lithium 8. So these percent abundances are just telling you how often it occurs in nature. To get this relative atomic mass, we have to do a weighted average, which is what we did with the dogs, right? So what we're doing is we're multiplying the abundances here times the relative masses, which would be like 6, 7, or 8, and then adding those together and dividing by 100 because these percentages are out of 100, right? They add up to 100. So for instance, for this lithium, we do the abundance of lithium 6, so 7% of our lithium is lithium 6, so 7 times 6, plus the abundance of lithium 7, 92 times 7, plus the 1%, right, times lithium 8. Add those all up, divide by 100, you get 6.94, right? So this is a weighted average, and we call it the relative atomic mass. Because it's relative, it doesn't actually have units. But this number will come into play later as we start talking about moles and grams per mole and all that. But for now, we can think of it as a unitless thing because it's relative. But this is your formula, right? Abundance times relative mass plus abundance times relative mass. However many you might have 2 isotopes, you might have 10 isotopes. And then you divide it all by 100. So